A better understanding of the properties of steam may be achieved by understanding the general molecular and atomic structure of matter, and applying this knowledge to ice, water, and steam. A molecule is the smallest amount of any substance, still possessing all the chemical properties of that substance which can exist. Molecules themselves are made up of even smaller particles, called atoms, which define the basic elements such as hydrogen and oxygen. The specific combinations of these atomic elements provide compound substances. One such compound is represented by the chemical formula H2O as seen here, having molecules made up of 2 atoms of hydrogen and 1 atom of oxygen. The reason water is so plentiful on Earth is because hydrogen and oxygen are amongst the most abundant elements in the universe. Now, most mineral substances can exist in the 3 physical states: solid, liquid, and vapor. These physical states are referred to as phases. In the case of H2O, the terms ice, water, and steam are used to denote the 3 phases respectively. All the 3 phases of a particular substance can only coexist in equilibrium at a certain temperature and pressure, and this is known as the triple point. The triple point of H2O, where the 3 phases of ice, water, and steam are in equilibrium, occurs at the following temperature and pressure. Note here that this absolute pressure is very close to a perfect vacuum. If the pressure is reduced further at this temperature, the ice, instead of melting, will sublimate directly into steam. The following experiment provides valuable insights into the triple point of H2O. In ice, the molecules of H2O are locked together in an orderly lattice-type structure, as depicted here. In this solid phase arrangement, the molecules can only vibrate. The continued addition of heat causes the vibration to increase to such an extent that some molecules will eventually break away, and the solid starts to melt to a liquid state. At atmospheric pressure, melting occurs at 0 degrees Celsius. Changes in pressure have very little effect on the melting temperature, and for most practical purposes, 0 degrees Celsius can be taken as the melting point. However, the melting point of ice falls by 0.0072 degrees Celsius for each additional atmosphere of pressure. For example, a pressure of 13.8 atmosphere would be needed to reduce the melting temperature by 0.1 degrees Celsius. For most substances, the density decreases as it changes from the solid to the liquid phase. However, keep in mind water is an exception to this rule, as its density increases upon melting, which is why ice floats on water. In the liquid phase, the molecules are free to move, but are still less than 1 molecular diameter apart due to mutual attraction, and collisions occur frequently. More heat increases molecular agitation and collision, raising the temperature of the liquid up to its boiling temperature. The enthalpy of water, or liquid enthalpy, or simply sensible heat of water, referred to as H sub F, is the heat energy required to raise the temperature of water from a reference point of 0 degrees Celsius to its current temperature. At this reference state of 0 degrees Celsius, the enthalpy of water has been arbitrarily set to 0. The enthalpy of all other states can then be identified relative to this easily accessible reference state. Sensible heat was the term once used because the heat added to the water produced a change in temperature. However, the accepted terms these days are liquid enthalpy or enthalpy of water. At atmospheric pressure, water boils at 100 degrees Celsius, and 419 kilojoule of energy are required to heat 1 kilogram of water from 0 degrees Celsius to its boiling temperature of 100 degrees Celsius. It is from these figures that the value for the specific heat capacity of water of 4.19 kilojoule per kilogram degree Celsius is derived for most calculations for water between 0 degrees Celsius and 100 degrees Celsius. As the temperature increases and the water approaches its boiling condition, some molecules attain enough kinetic energy to reach velocities that allow them to momentarily escape from the liquid into the space above the surface, before falling back into the liquid. Further heating causes greater excitation, and the number of molecules with enough energy to leave the liquid increases. As the water is heated to its boiling point, bubbles of steam form within it and rise to break through the surface. Considering the molecular structure of liquids and vapors, it is logical that the density of steam is much less than that of water, because the steam molecules are further apart from one another. The space immediately above the water surface thus becomes filled with less dense steam molecules. When the number of molecules leaving the liquid surface is more than those re-entering, the water freely evaporates. At this point, it has reached boiling point or its saturation temperature, as it is saturated with heat energy. If the pressure remains constant, adding more heat does not cause the temperature to rise any further, but causes the water to form saturated steam. The temperature of the boiling water and saturated steam within the same system is the same, but the heat energy per unit mass is much greater in the steam. At atmospheric pressure, the saturation temperature of water is 100 degrees Celsius. However, if the pressure is increased, this will allow the addition of more heat and an increase in temperature without a change of phase. Therefore, increasing the pressure effectively increases both the enthalpy of water and the saturation temperature. The relationship between the saturation temperature and the pressure is known as the steam saturation curve. The steam saturation curve is now shown on screen. Water and steam can coexist at any pressure on this curve, both being at the saturation temperature. Steam at a condition above the saturation curve is known as superheated steam. Temperature above saturation temperature is called the degree of superheat of the steam, as depicted here for superheated steam at point A. Water at a condition below the curve is called sub-saturated water. Okay, now if the steam is able to flow from the boiler at the same rate that it is produced, the addition of further heat simply increases the rate of production. If the steam, however, is restrained from leaving the boiler and the heat input rate is maintained, the energy flowing into the boiler will be greater than the energy flowing out. This excess energy raises the pressure, in turn allowing the saturation temperature to rise as the temperature of saturated steam correlates to its pressure.